Derivatives of logarithmic functions. Goals here: know how to find the derivative of a logarithmic function and be able to use logarithmic differentiation, which we're going to see is a useful technique for certain types of functions. So starting out, derivatives of logarithmic functions. The process of finding the derivative of logarithmic functions relies on the knowledge of logarithms and implicit differentiation. So overall, what we're really looking to do here is find the derivative with respect to x of this log base a of x. So that's what we're going to start with. Now, what we're going to do is let y equal log base a of x. And if that's true, then by the definition of logs, you're going to have this a to the y equals x. And the reason we're going here is because we don't know the derivative of the log. I mean, that's the whole point of this video. So we need to use something that can rely on prior knowledge. And the a to the y equals x will allow for some prior knowledge to be used. And in fact, I'm going to go ahead and take the derivative of that equation and use implicit differentiation in order to get the derivative of y with respect to x, which essentially then will be our y derivative, or our log base a of x derivative. So implicit differentiation, the derivative of a to the y is going to be using our derivative of exponentials. It's going to be a to the y, natural log of a. And then since I'm taking the derivative of something that has the y in there and it's not the respected variable, that's where that implicit idea comes in. That y is like some unknown inner function of x. You haven't used a chain rule. We'll multiply that first part by the dy dx derivative. And then on the right side, you just get 1. So now I can solve for dy dx by dividing both sides by that a to the y, natural log of a, and I get this 1 over a to the y, natural log of a. And that's all well and good, but I want dy dx, and this final form is in terms of a y, so I need to go back up here and use the fact that I have that a to the y equals x, and then we get our final answer, dy dx equals 1 over x times the natural log of a. So that is our derivative of y, which our derivative of y is essentially giving us our derivative of the log base a of x. So to put this together then, the derivative with respect to x of log base a of x is going to be equal to 1 over x natural log of a. And that's the important thing to remember here. All right, one thing to note moving forward with this is that if your base a is actually the natural number e, the 2.718, etc., 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 then you get, if we kind of start this out, d dx. And when you have the base e, that's really the natural log. So you got this natural log of x. And I'm going to go ahead and write this out a little bit more explicitly with the, you don't usually write it this way, but just to, make it stand out. This is the log base e. So when you do the derivative using the form that we just developed up above, you get 1 over this x natural log of the base, which is e. Well, natural log of e is really saying what power do you raise e to get itself, and that would just be 1. So natural log of e is just 1, and you end up with 1 over x. Or more concisely, putting this all together, when you have the derivative of the natural log function, natural log of x, you just get 1 over x. This is the only base that you will see that for, because it's the only base that'll make that natural log of a aspect essentially go away and just become 1. So this is also a very important thing to remember, and probably more important than the one above, because calculus loves the base e because of that. You don't have to worry about that extra natural log of a part. Okay, so we got some derivatives then of our logarithmic forms. So let's take a look at logarithmic differentiation. And in logarithmic differentiation, it's useful for functions that have a variable base and exponent. So an example of this type of function might be something like this, where you got f of x equals x to the x power. And note that this is not in the form x to the n, where n is actually a number, or a to the x, where a is actually a number. So we can't use the power rule or the rule for deriving exponential functions. It's just not going to work. X to the x is a different beast than x to the n or a to the x. However, we can use logarithms and their properties to rewrite the expression and find the derivative implicitly. So we're going to start out here and just use that example function. And this process will work really for any type of function that has this variable relationship, where you got a variable in the base and a variable in the exponent. This process will work every time. And what you do is, you start out like I did here, y equals x to the x, and then I'm going to take the natural log of both sides. And you may have done something like this in college algebra or some other algebra class, where you were solving for the power. You introduced the log on both sides, and the reason you did that is because you could then use the log property where the power can actually be brought out front as multiplication. And now from this step, I'm going to go ahead and do the derivative, and we'll have this natural log of y equals x natural log of x equation as being what my goal is to find the derivative of. And I'm going to use implicit differentiation. So on the left side, we got the natural log of y. The derivative of that is just going to be 1 over y. It's got that nice base e. And then since the y is not the respective variable, we're thinking about it in terms of that chain rule idea where y is some unknown function of x. So I need to multiply then by its derivative, dy dx, whatever that ends up being. And then on the right side, we got to use the product rule. So we'll have x going to 1, and then just natural log of x, and then plus x times the derivative of the natural log of x is just 1 over x. And we're getting close here. So almost there to find this dy dx, and I'll multiply both sides by y so I can get that dy dx alone, and I'll have this natural log of x plus x times 1 over x is just going to be 1. And now we go back up a little bit and recall that y was this x to the x. So to complete the derivative of x to the x, this dy dx that we're finding here, you just replace that y with x to the x, and then times this natural log of x plus 1. And that would be your answer. So again, to recap the steps here, you start out by letting the y equal that expression that has the variable base and variable power. Introduce the natural log on both sides, and I use the natural log because it has a nicer derivative than the log base a, the general form. And then we can move that power, that troublesome power, out to the front. And that's really the key reason why we introduced the log on both sides. And then we can just use implicit differentiation from there in order to find our final answer for dy dx. Right, so you might be doing some of those in class, so make sure that you understand those steps, and thank you for watching.